Good morning, USM! All right, that might have been exuberant, but 5 extra points on your quiz for whoever can tell me what I used as inspiration for that opening. Well, curious how many of you are going to get that. All right. For today's video, we're going to start to look at some of the simplest types of alkanes, alkenes, and alkynes. Look at some of the properties of those hydrocarbons, and then we're going to start to really get into the naming conventions and how we start to name things. And so we're going to start off with alkanes. Let's take a look at some of the various ways that we represent hydrocarbons. And so we can write things as Lewis structures, which we're familiar with. And so if we had, for instance, a 5-carbon chain, if we had pentane, then this would be our Lewis structure for it. So there's all of our carbon atoms with our hydrogen atoms hanging off there. So C5H12, and hopefully at this point you would all be able to write that Lewis structure. We also write what we call condensed structures, where now for a condensed structure, we don't actually bother writing in the bonds. And so we just write, we can see here on the end is what we call a CH3 group. So a carbon with our 3 hydrogens. So there's our CH3, followed up by a CH2, a CH2, a CH2, and we see those 3 right here, and then lastly our CH3. And so that's our condensed structure, just not writing in the bonds, but knowing that this CH3 is on the end here, and we have our CH2, and that all these carbons are bonded together in a chain. We can also write what we call an abbreviated condensed structure, where now instead of writing out all 3 of these CH2s, we're going to write CH2 and then subscript 3. Just indicate that we actually do have 3 of these right in a row. And so this is a way for us to just simplify how we write compounds without having to write the full Lewis structure out every time. Still gives us all the information, tells us what we have in there for atoms. We just have to use a little bit of logic and figure out how they are actually connected to each other. We know that, for instance, that hydrogens are only ever going to form 1 bond, so they're always going to be on the outsides. And then the carbon is going to make up our chain in the middle. We also have, and this is a lot of the information we just talked about, we also use what we call line structures. In line structures, we actually show all the bonds, but we don't write most of the atoms. This is going to simplify things for us even further. So in a line structure, we don't write carbon or hydrogen atoms. Every point or every vertex in a line structure instead is known to represent a carbon atom. And the hydrogens are assumed to be there in order to complete our octets. And so, for instance, here we have a Lewis structure for propane. If we were to write a condensed structure for that, it would simply be CH3, CH2, CH3. But here's our line structure for propane. And so right here at this vertex, at this point, this is a carbon atom. And it's understood that there would have to be 3 hydrogens coming off that carbon atom in order to form its octet. Here at this vertex, here's a carbon atom. And again, understood that there must be 2 hydrogens coming off that for it to have its octet. And then down to this point, another carbon atom, and it must be a CH3 for its octet. So we have 1, 2, 3 carbons. Octane, C8. Here's our long drawn out Lewis structure. What we can see here, we have 1, 2, 3, 4, 5, 6, 7, 8. When you're drawing these, one thing to keep in mind is that the first point is a carbon atom. So let's say you wanted to draw out the skeletal structure for C4H10. It's tempting, and I did this when I was first learning this. It's tempting when you start out. We're going to start with our point right here. Tempting to then say, okay, 1, 2, 3, 4. But we can see here that this is actually 1, 2, 3, 4, 5. And so this would not be correct. What I would recommend you do is just say 1 to yourself when you first put your pen down. 1, 2, 3, 4. So here is now our skeletal structure for butane. And again, we always assume that there are the number of hydrogens coming off there, of each of these carbons. Sorry, I'm writing hydrogen very crudely. But there are the number of hydrogens coming off there to complete our octet. If we were to write a condensed structure for this, we have our CH3, CH2, CH2, CH3, or an abbreviated condensed CH3, CH2, 2, CH3. But that's how we draw skeletal structures. And so remember that at every point or vertex, that represents a carbon atom. And we assume a number of hydrogens to complete our octets. And these are just some of the basic rules. It might be tough to see on your screen, but you can certainly pause the video and zoom in on this a little bit in order to see some of the various rules that we have. But some of these, a lot of these, we'll be talking about as we go on through talking about some of our different types of structures as we move on. We also have what we call cycloalkanes. A cycloalkane simply means that it's an alkane that now is going to come around and form some sort of ring structure. And so let's say that I have a 5-carbon wow, can't spell today. 5-carbon cycloalkane. So I know now that I'm just going to have 5 carbons, but they're going to be all connected in a ring. And so I'm going to have 1, 2, 3, 4, 5, and then coming back to connect in a ring. So your basic pentagon shape. A 6-carbon cycloalkane. Same idea, but now I'm going to have 1, 2, 3, 4, 5, 6, and then connected back to the first. Again, with our appropriate number of hydrogens hanging off all of those carbons. And so that's a cycloalkane, and we're going to talk about these naming conventions actually right now. So this begins our look at how we name organic compounds. Talked about a little bit in the last slide, but we're really going to start diving in now because this is a big part of what we're going to be discussing in the next few lectures, really, in looking at various different types of organic compounds. We're going to be diving pretty deep into how we name them. And so remember, as I said in the last lecture, there are 3 parts to every name. There's our prefix, there's our root, and our ending. The prefix is for naming things that are attached to the main chain, or for letting somebody know that we're talking about a cyclocompound. We're going to focus more on that in our next lecture when we start talking about substituted hydrocarbons. For now, our prefix, we're just going to look at a couple cyclo examples. But that's the whole idea of the prefix, is by identifying and naming things that are coming off of our main chain. The root, that is our main chain. That is our primary chain. And so we identify the root and we name the root by the number of carbon atoms in that main chain. That was the big table that I had you look at in the last lecture that I told you to memorize. And so if there's only 1 carbon there, our root is meth, 2 carbons is F, 3 carbons is prop, and so forth. That's the root of our name for organic compounds. The ending is whatever the primary or most important functional group is in the compound. We'll talk more about functional groups later on. For now, know that functional groups are really sort of what give a compound its main chemistry, its main behavior. We've already kind of talked about some. Alkanes, alkenes, and alkynes are all examples of functional groups. And so an alkane is a compound that has just carbon and hydrogen in it with all single bonds. An alkene has 1 or more double bonds, and an alkyne has 1 or more triple bonds. And the ending for any compound is determined by what group it is. So the ending for any alkanes is simply ane. Let's look at a couple examples. So here we have a compound here. We would start by counting the number of carbons. We're going to count up and say 1, 2, 3, 4 carbons in this chain. So our root for this compound is bute. Again, we need to have that chart memorized if you haven't by now. So our root is bute, and our ending, since this is just carbon and hydrogen, all single bonds, that tells us that it's an alkane. So our ending is ane, leading us to the full name of the compound of butane. Here in this example, we start with our root, 1, I'll start right here, go clockwise, 1, 2, 3, 4, 5, 6, 7, 8 carbons long. So our root is oct, all carbon and hydrogen in this, and all single bonds. So our ending is ane. We also see that this is connected into a ring. And so that's going to give us the prefix of cyclo, putting our full name together of cyclooctane. Now you'll note that especially in this last example, I didn't just start with the prefix and then go to the root and then go to the ending. I didn't just kind of go straight across. I started with finding the root. Then I figured out the ending, and then I worked out what the prefix would have to be. This is going to be our general strategy to name compounds as we move forward. And again, we're going to be focusing on a lot of different naming conventions in the next few lectures. And so that's the general strategy that you do want to keep in mind. Find your root first, find the longest carbon chain, and we'll look at some more complicated examples of that in subsequent lectures. But that's your basic pattern. Find your longest carbon chain first, there's your root, then go on from there and name the rest of the compound. Alkanes can freely rotate around their bonds. And what I mean by that is, let's take a look at an example here. So here we have just simple hexane. 1, 2, 3, 4, 5, 6 carbon atoms here. And so if we were to draw just a line structure of this, it would just look exactly like it does in my hand here. 1, 2, 3, 4, 5, 6 carbons. And so the name for this would simply be hexane. These bonds, though, can all freely rotate. And so hexane might be shaped more like this. And so that would look, again, if we were to draw sort of what that looks like in the line structure, we would draw it like this. It's still our same 6 carbon atoms, 1, 2, 3, 4, 5, 6 carbon atoms, still those same number of atoms, but a different, what we call, conformation. And so either one of these would technically be correct. Hexane could exist in either form. By convention, we always write out in this zigzag form. That's just how we draw it out. Makes it easier to see that. And so we'll always try to draw out just in our straight up zigzag form like this. We can also have compounds that have the same exact molecular formula, but the atoms are actually bonded together differently. These are called structural isomers. They will have different physical and chemical properties from each other. Let's actually look at an example here. So for instance, pentane. Take one of these carbons off here. So here we have pentane. So 1, 2, 3, 4, 5 carbon atoms. Now I could take this carbon atom on the end off. And the chemical formula for this, like it says there, C5H12. I could take that carbon atom off and instead attach it right here in the middle. It's still 1, 2, 3, 4, 5 carbon atoms, and if we count out the number of hydrogens, there would still be 12. Same exact chemical formula, but the atoms are now connected to each other differently. That's a structural isomer. I could even go further. Take this one off, and oops, looks like I don't have a carbon atom attached here. Let me just play with this a little bit. Hold on just a second. I just need to fix something here. I think this should do it. Here we go. Now, I still have 1, 2, 3, 4, 5 carbon atoms, and I would still have 12 hydrogens. I'd have 3 each on each of these outer carbons, so the chemical formula is the exact same. Very, very, very different shape. Remember what we talked about in the last lecture with our boiling points and our melting points. This version of pentane would have a lower boiling point than this version of pentane. Same exact chemical formula. Structural isomers, so they'll have different properties. And we can see the same thing with the hexane down below. I won't show all of those, but we'll look at a couple. So there's our straight up zigzag hexane, just the straight chain. This carbon on the end could actually be attached right here. It could be attached right here. Same chemical formula, but now our structures are very different. We could have, I guess I will show you all of them. Why not? We could have this. Still the same exact chemical formula. It's still the same exact chemical formula. We attach like this. Get in there. But very different properties. So they're structural isomers of each other. And we're going to talk about how we would name those in a little bit. This would be straight up pentane here, and this would be straight up hexane. These others would not get those same names, and that's a large part of the subject of our next lecture. From alkanes, we now move on to alkenes. So an alkene will contain one or more carbon-carbon double bond. An alkene that has 2 double bonds is called a diene. An alkene with more than 2 double bonds is called a polyene. A great example of that, here's beta carotene. Beta carotene is probably something that sounds familiar to a lot of you. It's a big source of vitamin A. It's one of the better nutrients in carrots that's very good for you. And so we see here many, many, many carbon-carbon double bonds, whole bunches of them. And this would be considered a polyene. Alkynes, one or more carbon-carbon triple bonds. Alkynes will always have a linear shape around the carbons making up the triple bond. Naming for alkenes and alkynes. Remember, our general naming convention, prefix, root, ending. The ending for an alkane, if it's all carbon, hydrogen, single bonds, the ending for an alkane will be ane. Ending for alkenes, if there's one or more double bonds, is ene, E-N-E. The ending for alkynes, if there's one or more triple bonds, yne, Y-N-E. And so, and we'll talk about the second part in just a second, but a couple examples here. So we still start with our root. How many carbons are in our longest chain? And so right here, in both of these, 1, 2, 3, 4 carbons long. So we get bute, and our ending is ene for both of these because they're alkenes. Here we have 1, 2, 3, 4, 5 carbons, so our root is pent, but there's a triple bond in here, so it's pentyne. With alkenes and alkynes, we also have to tell in the name where the multiple bond is located. This compound is very different from this compound, just by virtue of having a double bond between 2 different carbons. And so this one is 1-butene because the carbon-carbon double bond is after the first carbon. Now, some of you might be saying to yourself, what are you talking about, Mr. Staples? That's not the first carbon. This is the first carbon. The other part of naming compounds is that we always number the atoms in such a way to end up with lowest numbers for our prefixes. And so if we started numbering right here, actually, let's come over to here. So let's just redraw that. So we have this compound right here. So we have two choices for how we number these carbon atoms. Either 1, 2, 3, 4, or we can start over on the right-hand side and number opposite. We're always, always, always going to choose the numbering convention that gets us to the lowest number. And so, again, recognizing that we have to identify where our double bond is, and we always identify that number as where the double bond starts, then if we used our numbering convention in red, starting from the left, we would end up with 3 butene. If we use our numbering convention in blue, we end up with 1 butene. And so that's going to be our winner. And so we're going to number from right to left. So you always want to set up your numbering to get to the lowest number possible for your numbering conventions, for your prefix. The other option would be a double bond in the middle. And so that wouldn't matter which way we numbered. Either way, 1, 2, 3, 4, or 1, 2, 3, 4. We're going to come up with our double bond between the second and third carbons. Gets us to 2 butene. 1, 2, 3, 1, 2, 3, 4, 5 carbon atoms here. Our triple bond is between the second and third, so it's after the second carbon. So we get 2 pentyne. Simple, right? Not so bad so far. Now, remember how I said with alkenes, let's just sort of redo this one a bit. Sorry, with alkanes, rather, I'd said that they can rotate around these bonds all day. So, I mean, this one could really even be set up like this, or it could be like this. I mean, any, excuse me, any conformation. But because these single bonds can rotate all day long. Double bonds can't do that. So here's 1, 2, 3, 4. Here is our 2 butene from the last. This is just a representation of this molecule right here, our 2 butene. 1, 2, 3, 4 carbons, double bond between the second and third. So that's 2 butene. This can't rotate in that same way. This compound is stuck in this conformation. And so when we're naming something like this, what we have to do now is also identify a difference between these 2 molecules here. Hold those in such a way that you can actually see them. And so our difference here, look at this one. In this one, again, since these can't rotate, we sort of look at where the plane of our double bond. So if we're looking at the plane of these 2 carbons, in this example, we have another carbon group below the molecule and another carbon group above the molecule. And so we have these 2 large carbon groups on opposite sides, as opposed to this one. 2 large carbon groups now on the same side. Again, because it cannot do this. We can't twist it around. I can't even do it with the model. It doesn't let me. And so we have to identify that because these 2, believe it or not, are going to have different properties from each other. And so the naming convention for what we have to do there is cis and trans. Cis, if our important groups are on the same side. Trans, if our more important groups are on different sides. It sounds silly, but another way that I remembered that when I was first starting out is same side cis, or same side cis. Sounds very familiar. Same side cis. You don't really have the same thing with trans, but different side trans. And so again, we have our 2 different names now. We have cis 2-butene or trans 2-butene. hold it like that because it's the same way that it is in your slide. So cis-2-butene, trans-2-butene. And so the way that you would just go about those, let's say it wasn't just carbon groups. Let's say we have maybe oh, I don't even know what else. Maybe this is just another carbon coming there. Actually, yeah, I'm doing this one off the top of my head, so let's just sort of regroup here. Here's our double bond, and there's our, yeah, there we go. We'll draw it like that. So we want to name this compound. And so there's a couple ways. Actually, we're not going to worry about the full namings. We're not going to get into the bromo yet, but we are going to worry about if this is cis or trans. Let's draw in our hydrogens, because that might make this one a little bit easier. So we're going to draw in our hydrogens. We can see our double bond right here. So here's our double bond. And so what we want to do is we want to kind of draw or think of a plane coming down through our double bond. And one way that you can go about this is just sort of ranking the things that are attached to the carbon by what is bigger. And so over on this, if we look at this side here, we're looking at this carbon right here, our second carbon, then we see that this second carbon has another entire carbon group attached to it, and it has a hydrogen attached to it. So we can say pretty confidently that this one is bigger than this one. So we're just going to rank those 1, 2. Now we look at this carbon here, and we see that this carbon has a bromine and it has a hydrogen attached. And so again, we can see that the bromine is bigger than the hydrogen. And so we're going to rank this as a number 1 and this hydrogen as a number 2. And so we can see that our number 1 things are things that are bigger, are on opposite sides of the double bond. And so this compound, we get the trans designation. As opposed to, too many bonds there. As opposed to this compound, we would go through the same sort of analysis. Writing in your H's sometimes helps with these. We're going to say here's the plane of our double bond. We rank things on the carbon. We see that this is more important than this. This is more important than this. And so now we see that the more important things are on the same side of the double bond. And so this gets the cis designation. We're not going to worry as much about the full naming with the bromine. That'll come later when we talk about some different naming rules for some other types of compounds. But I really wanted to show just another example with cis and trans and how we would identify that, because we do have to identify that with in the cases of having different things coming off our double bonds. Now, let's just take a look back at 1-butene. We don't have to worry about cis-trans with 1-butene, and let's take a look at why. With 1-butene, so here's our 1-butene. Here's the plane of our double bond. When we draw in our hydrogens, we can see that on our 1 position, it's both hydrogens. And so those are going to be equal importance. And so we don't have that issue of the more important things being on one side or the other, because these have an equal importance. So we don't worry about cis or trans in this case in the same way that we would have to worry about cis-trans in a case like this, or even longer. Let's say this compound was longer and had other stuff going on. Believe it or not, we're going to learn how to name something like this in just the very next lecture. Not as hard as it looks, but we would have to worry about cis-trans with a compound like this. But we would not have to with this one, in which we have the same groups coming off one of the carbon atoms. And so that's all for our alkanes, alkenes, and alkynes, lions and tigers and bears, oh my. In the next lecture, we're going to get even deeper into naming and look into naming things like that second compound that I shared. Did I switch over for that one? I don't remember if I did. I don't think I did. So sorry, I drew a bunch of that out and you didn't even see it, I think. But there it is. You can take a look back at that, what I was talking about. And so that is it for today's lecture. And so I wish I'll just leave you with everybody stay groovy like a drive-in movie.